Contingency Tables. This section shows how to use chi-squared to test the relationship between nominal variables for significance. The data in the table are from the case study, Mediterranean Diet and Health, and show the relationship between diet and health outcomes. Some of the subjects followed the low-fat diet recommended by the American Heart Association, while others followed a Mediterranean-type diet consisting of more bread and cereal, more fresh fruit and vegetables, more grains, more fish, fewer deli foods, and less meat. The adverse health events of cancer, fatal heart disease, and non-fatal heart disease were recorded over a 4-year period. We can see that the American Heart Association diet led to more adverse health events. The question is how to test the differences in frequencies for significance. The first step is to compute the expected frequency for each cell based on the assumption that there is no relationship between diet and health outcome. You can see that 22 of the 605 subjects developed cancer. The proportion who developed cancer is therefore 22 over 605, which equals 0.0364. Therefore, if there were no relationship between diet and outcome, we would expect 0.0364 of the subjects to develop cancer regardless of which diet they were on. Since 303 subjects were on the AHA diet, we would expect 0.0364 times 303, which equals to be 11.02 cancers on the AHA diet. Similarly, we would expect 0.0364 times 302, which equals to be 10.98 cancers on the Mediterranean diet. Notice that there were more cancers than expected in the AHA diet, 15 versus 11, and fewer than expected on the Mediterranean diet, 7 versus 11. In general, the expected frequency for a cell is equal to the row total for the cell times the column total for the cell divided by the total number of observations. For example, to compute the expected frequency for cancer in the AHA diet, you multiply the row total of 303 by the column total of 22 and divide by the total of 605. The result is 11.02. The expected frequencies for each cell are shown in parentheses. As in the case of one-way tables, chi-square is computed by, for each cell, squaring the difference between expected and observed frequencies and dividing by the expected frequency. These values are then summed. For example, for the AHA cancer cell, the expected minus observed is 3.98. The square of 3.98 is 15.84. Dividing this by the expected frequency of 11.02 gives 1.437. The chi-square is the sum of these calculations for the 8 cells. For these data, chi-square equals 16.55. The degrees of freedom are computed by multiplying the number of rows minus 1 by the number of columns minus 1. In this case, there are 2 rows and 4 columns, so we multiply by 2 minus 1, which is 1, by 4 minus 1, which is 3, obtaining 3. In the formula for degrees of freedom stands for degrees of freedom, R stands for the number of rows, and C stands for the number of columns. The chi-square calculator can be used to determine that the probability of a chi-square of 16.55 or larger with 3 degrees of freedom is 0.0009. Therefore, the null hypothesis of no relationship between diet and outcome can be rejected. A key assumption of the chi-square test of independence is that each subject contributes data to only one cell. Therefore, the sum of all cell frequencies in the table must be the same as the number of subjects in the experiment. Consider an experiment in which each of 16 subjects attempted to anagram problems. It would not be valid to use the chi-square test on these data since each subject contributed data to two cells. One cell based on their performance on anagram 1 and one cell based on their performance on anagram 2. The total of the cell frequencies in the table is 32, but the total number of subjects is only 16. The violation of the assumption of independence occurs because a subject who is able to solve anagram 1 is probably more likely to solve anagram 2 than a subject who failed to solve anagram 1. From the formula for chi-square yields a statistics whose distribution is only approximately a chi-square distribution. The approximation is adequate, or at least conservative, when the total number of subjects is 20 or more. Some authors claim that the correction for continuity should be used whenever an expected cell frequency is below 5. Research in statistics has shown that this practice is not advisable. The correction for continuity when applied to 2x2 contingency table is called the Yates correction. The stimulation 2x2 tables lets you explore the accuracy of the approximation and the value of this correction.